Hey everybody, welcome back to another round of physics. Yeah, let's get going. So I figured I would have for you here a situation where we have not individual point charges, but rather we have a distributed charge. So I'll go ahead and draw that situation for you. So pretend that you have a distributed charge, say something like a total charge of Q distributed over a length of what we'll say is 2L. Now, to set up the problem, we'll go ahead and let's put a y-axis right here, and we'll bisect the bar, and we'll run the x-axis along, say, to the right. And then the last thing that we're going to consider is that we have our field point down here, which we will just call little q. And yeah, I guess we probably need at least one more dimension here. Let's go ahead and say that little q is located a distance y naught below the wire, or the line charge. And so now the question is, how do we go about finding the Coulomb force between the bar and this little point charge? Okay. And that's what we'll run through with the video, but remind yourself real fast, kind of the steps that we followed in order to find the Coulomb force between two point charges. Okay? Yeah, okay, good, good. So pause the video. I mean, like you should go through and kind of think about that process there. But essentially that process was something along the lines of find the relative position vector between the two charges. And then after you find the relative position vector, you can find the magnitude of that relative position vector. And once you have the magnitude of the relative position vector, you can find the magnitude of the Coulomb force. Okay. Now, of course, the force is a direction. And so number 4 would be using the magnitude of the Coulomb force and the magnitude, specifically r hat, which is given by the relative position vector over the magnitude, you can now find the vector force, right? So this allows you to find the full complete vector force. And then number 5, you could take a summation, right? If you have more than one point charge in your surroundings, then you can just rinse, wash, and repeat for all of the point charges. Okay? Now, we are going to follow the exact same process, okay? Pretty much verbatim, okay? With a tiny, tiny little change, because the issue here is that we don't have a single point charge. We have, if you will, an infinite smearing of point charges. So one of the first things that we should probably figure out is what do we call, say, how much charge is involved in just that tiny little segment of the bar. And so I'll introduce a new concept here, or at least a new terminology. And the idea is that we will assume that there is uniform charge density. In other words, for this bar, if I take a small segment that has some width, and I'll call that width dx, we'll call that width dx, any dx, any width dx that I take anywhere along that bar will have the exact same amount of charge. Now, this is referred to as a linear charge density because we're talking about charge smeared out across a one-dimensional object. And usually the Greek letter that's reserved for that is lambda. So linear. Whereas let's say you have a charge per unit area, that is usually lowercase sigma. I'll say area. And if you have a charge per volume, that usually is rho. Okay. So these two we generally won't deal with in 186, But when we get to 332, for example, you'll certainly see more of this volume charge density. Maybe we'll do an area example just for, kicks, but certainly the volume charge will probably wait until later. Okay. Now, the fact that it's a uniform charge density, what that means is I can say lambda is equal to lambda. Okay, kind of the most unhelpful math equation that we could write. And let's think about this. What this really means is charge per unit length. Okay. So over here on the left-hand side, I can say the total charge of the bar divided by the length of the bar, say 2L. And over here on the right-hand side, I'll say that there's this unknown charge, this infinitesimally small charge associated with this infinitesimally small segment of the bar. So this infinitesimally small charge associated with this infinitesimally small length of the bar. And so now I have an expression for that small piece of the bar. That small piece of the bar, that is a length of dx, has this much charge contained in that infinitesimally small piece. So we'll go ahead and box that. We're going to want that later. Okay, so that's kind of the one small little change. So now let's go through and think about, well, our little steps that we've written out here. For the position, this blue box, this small infinitesimal piece that I've indicated, we see that the relative position vector pointing from that box to our field point. Okay. Yeah, you can see certainly the y component. We'll say the y component, you certainly see we need to go in the negative y naught direction, or excuse me, the negative y direction by y naught distance. And so we really need to think about how do we express the location of this little slice that we've taken. And bear in mind, thinking towards the future, we are going to want to vary the location of that slice, right? That's step 5, vary the location. Okay. I will go ahead, and as I've already kind of hinted at with some other places, I'm going to go ahead and just use the variable x. Now notice, x is a variable. We're going to change that for each location. Y naught is a constant, right? It's the distance of the field point below the bar. Okay. Now you say, where have I already hinted that I was going to use x as a variable? Right here, when I took my expression for the infinitesimally small charge, I called the distance dx, and that will be what we refer to as the integration variable. I am going to change the value of x, and I should ask you, ranging from what value to what value? Yeah, ranging from negative L all the way up through positive L, the whole length of the bar. Okay? So good. We have now an expression for our relative position vector, and notice it is written in terms of a variable, so this could arbitrarily be applied to any small line segment on that bar. So now what we need to do, well, I imagine that finding the distance is not too much of a stretch, right? Yeah, go ahead and write that down. You get something like this. Right? And of course, the negative sign that's in the y component, when I square it, we lose that negative sign. Okay, well, how about the Coulomb force? Now, please notice that I am talking about the infinitesimally small contribution to the total force, the net force, due to this infinitesimally small point charge. Okay? So right now, I will label it as dF. Okay? And we'll go ahead and we'll combine steps 3 and 4. So the Coulomb force says that we would take the Coulomb's constant times our system charge. And here, remember, we're talking about an infinitesimally small charge on the bar divided by our relative position vector squared. So there's the magnitude. And then, yeah, we have this r over the magnitude. So I'll write it like this, okay, instead of writing it as a unit vector. We'll go ahead, let's substitute in everything, right? We have k and q, those are just given constants. Our dq, well, that is the total charge of the bar divided by the total length of the bar, 2L, times dx. Okay. And then what do we have? Well, the vector, we had x comma negative y naught comma 0. And over, I'll write it like this, x squared plus y naught squared to the 3/2. And technically we're done, right? There we go. That is the small, infinitesimally small contribution to the total force. Okay. Now notice all of this rigmarole out in front, that's just a constant, right? And big parentheses there. And so really what I'm left with is figuring out, what do I do with this piece? Okay. Now, just like any vector problem that you usually have dealt with up to this point, this would be no different. Okay. I would like to take the summation of all the individual pieces. Okay. So I'm going to have to do an integral. Okay. And the question becomes, how do I do an integral of a vector? Well, treat it just like we've done all the other vectors. Let's break it into components. And so indeed, what we can do is that we will integrate, let's say I'll do f of x, and I will only look at the x component, 2L, and I'll have to integrate x over x squared plus y naught squared to the 3/2 dx, and that is the integral that I'll have to do. Oh, quick, limits of integration? Yeah, good. Say negative L to positive L. Okay. Similarly, if I want the y component, I will similarly have to perform an integration. Except now, instead of using the x component, I use the y. So the limits of integration stay the same, and I have a negative y naught dx over this rigmarole, x squared plus y naught squared to the 3/2. Okay. And yes, before you mention it, yeah, it is possible. Don't forget, x is essentially the location of each of our point charges along this bar, this one-dimensional linear charge. Okay? Y, when I have this y here, this is the component of the force pointing in the y direction. So it is perfectly permissible for components in, say, the y direction to depend on the x location of the charge. Okay. So x refers to the charge location, whereas this y that I've put in here, the subscript, refers to which component of the force you're talking about. Okay. Those two things are completely independent of each other. In other words, you can have, the y component of the force depends on x, the x position. Or the z component of the force could depend on the y position. And you could do all those. Okay? So the remainder of the video will be discussing how do we address these two integrals. Okay? Now, first off, I'll rewrite it here. Let's consider the x direction. So I had kq, big Q over 2L, integral of x dx, x squared plus y naught squared to the 3/2. And considering the physical situation, a bar, and we're right below the symmetry of the bar, right? The symmetry axis. Okay? What is this going to give me? What's the total value that this integral is going to give me? Yeah, 0. Good, right? You notice that for every chunk on this left-hand side, you could find another chunk here on the right-hand side, such that the two forces, say, I'll draw these in different colors so we can see them. You can say, well, those two forces will cancel in the horizontal direction and they will add in the vertical direction. And you can do that pairwise all the way through, right? For every little thin slice you can find on the left-hand side, there's a corresponding one on the right-hand side. So it's always good to remind yourself of that. Now we'll go through as practice to show that it is true, but later on you can certainly use those types of arguments to not even bother doing these integrals. Okay? Oh, it's symmetric and therefore the horizontal component will cancel. This will be 0. Okay? So yeah, let's go at it. Oh, excuse me. So that's one way. That's a physics argument. A second argument, if you want to make a math argument instead, is that notice right here, this integrand is an odd function. So you have to remind yourself, what are odd functions? Okay? So consider a generic function, f of x. Okay? That function is considered to be odd if f of negative x equals negative f of x. Okay? I'll say that again. If negative f of negative x is equal to negative f of x, probably the simplest odd function that you can think of is f of x equals x. Okay? You notice that if I plug in, so if f of x is equal to x, my function is x, then if I substitute, if I do f of negative x, right, f of negative x, that would be equal to negative x, which is equal to negative, and I'll pull that, right? You simply pulled the negative sign out of the parentheses. And this is just f of x with a negative sign out in front. Okay? Now you could check that, say x cubed. We'll do that one. Well, if f of x is x cubed, that means f of negative x is equal to negative x to the third, which is equal to negative 1 to the third, x to the third, which is equal to negative, and notice again, this is just f of x, negative f of x. Okay. Now here's the cool mathematical property. And you say, well, okay. Here's the cool mathematical property. Remember that the integrand, so I'll draw an odd function. We'll do the easiest one. When you do an integration, what is the integration actually doing? So you integrate a curve. Yeah, good. Excuse me. It is finding the area beneath the curve. So when you integrate, it's that you're finding this small area beneath the curve. Okay? So here's the next question, or here's the cool thing. Okay? Let's say I integrate about a symmetric interval. I don't know, something like negative L to L. Okay? Now, of course, this is not the function that we're dealing with here, but we have this. Okay? And you notice, what can you tell me? If you integrate an odd function over a symmetric interval, it will give you 0. Yeah, because for every piece, for every area, say on the left-hand side, this is a negative area, there will be a corresponding positive area on the right-hand side. Okay? So the integral of an odd function is equal to 0 if it is over a symmetric interval. So I'll say negative a to a. Okay. So that's the other way, really fast mathematically, how we can argue that this integration will give us 0. We'll go through and prove it. Okay. But let's go ahead and check. Is this function, if I call f of x, if I define it as being x over x squared plus y naught squared to the 3/2, okay? So is f of negative x, that would be negative x over negative x squared plus y naught squared to the 3/2. Well, that is just equal to, notice if I just, that's equal to negative, and I'll write over here, x over the negative sign squared gives me a positive. So that's positive x squared plus y naught squared to the 3/2, which is equal to this whole term right here is just my original function. So that is negative f of x. So this is indeed odd. Now, yes, for completeness, there are also even functions, and you already know what those are. It's if I substitute a negative value in, I get a positive value back out. Okay. And you notice that odd powers of x are all odd functions. Even powers of x, yeah, those all end up being even functions. Some other functions that are odd, sine of x is an odd function, whereas cosine of x is an even function. And tangent, what do you think? Tangent of x, which is an odd function divided by an even function, what do you think that's going to be? Yeah, good. Tangent of x will also be an odd function. Okay? When you take an odd function and when you take, say, the odd function divided by an even function, it's going to be an odd function still. Or an odd function multiplied by an even function. It's still going to be odd. Okay? So that's the other way that you can see. You notice that you have an odd function in the numerator and an even function in the denominator. So this whole thing will be an odd function. Okay? It's just to, get you going. Last thing for completeness, if odd, I'll put if odd. Okay, and I already had this. About a symmetric interval, f of x will be equal to 0. If it's even, then the integral over a symmetric interval of f of x will equal 2 times the half interval, so from 0 to a of the function. Okay. And the same thing, you can kind of get an idea for that. An even function, for example, would come down and then go back up. Okay. This is just an example. For example, the absolute value of x is an even function. And so then you can see, again, thinking about integrals being the area beneath curves, you can see that for every segment over here on the negative x side, there'll be another segment over here, also on the positive x side. Both of those are going to be the same area. Okay? So you could just do the 1/2 of the interval. Okay? Well, so let's get at it. So we already know the answer to this. Oops, excuse me. Just writing. We already know the answer to this. So let's go ahead and figure out how to show that. So negative L to L x dx x squared plus y naught squared to the 3/2. Okay. Go ahead. Run through your list of integration techniques. You got it? Yeah. So, and I encourage you, you should have a couple of integration techniques under your belt. You should always double check them. Things like U substitution, trig substitutions. There's integration by parts. There's partial fractions. And maybe repeated integration. That's repeated integration by part. You have some of those funky ones like logs or ln's or sines, sine, cosines. So there's some very particular ones that sometimes pop up. Okay. Yeah, so in this case, and it's always good to try them. Like you should give a try on them, keep fresh on them. But then, if none of these tend to work, I mean, I'm okay with you going and looking up a trig table or an integration table. Okay, because the issue is that you want to stay fresh on these techniques, but you don't want to have to spend 5 or 10 hours reinventing the wheel doing the math. Okay, so, but yeah, this one is simply solved by a u substitution. You say, well, how do I recognize that? Generally, the way I see it is that you notice that there's 1 power less in the numerator than in the denominator. Okay? That difference of 1 power sometimes screams u substitution. The other piece is that when you have like the added constant in, usually when you do a u sub, you can start like ignoring that constant, if you will. So let's go ahead. Let's get rid of this constant in the denominator. And how we're going to do that is we're going to set our variable, our u, equal to x squared plus y naught squared. Okay. Now go ahead and pause it. If you want to take a shot at this, go ahead, pause it, work through the rest of the problem. You got it? Okay. So yeah, so now we have du equals 2x. Bear in mind, y naught is a constant, and so when I take the derivative, I get 0. Nothing happens. Okay? Oh, excuse me. And I forgot, well, I have this 0, and don't forget, I have this dx here, right? I was taking a derivative. So now I see that if I take du and divide it by 2, I end up with the term x dx. And I'm in a position where I can take the u substitution, plug it in. I can replace the x dx in the numerator. And notice there's the clutch. There's the key, right? I have this x that pops out when I have to replace the infinitesimal length dx with this new variable du. Okay? So when I plug everything in, we get f of x equals kq, big Q, over 2L. I will not write in the limits because technically I should replace the limits for u instead of x. My personal preference is I'll do the integration and then I'll back substitute in terms of x to solve. Okay. That's just me. I don't like going through the work of finding the new limits. It's an extra calculation that I can just screw up on. So I'd rather convert it back to x usually. So what we have here, well, we have 1/2 du divided by u to the 3/2. Okay. And now you have to rack your brain. You say, okay, well, how do I do this? How do I do this? And this is just simply the power rule, right? We're undoing the power rule. The power rule for differentiation, if you recall, you take the power of x, put it down in front, and lower the power by 1. So you take the power of x and put it in front, and you lower the power of x by 1. Okay? Well, in this case, what we're looking at, oops, excuse me, I'll do it this way. Nxn minus 1, boy, muscle memory, dx. So I just move the dx to the other side, and I'm integrating this, essentially. Right? This is the piece that I'm integrating. So on this left-hand side, I would just get x to the n is equal to the integral of n xn minus 1 dx. Okay. Now here's we say, okay, well, what's the value of n gotta be? Yeah, you see it? Yeah, if I substitute in n is equal to 1/2, negative 1/2, then everything works. Right? If I go x to the negative 1/2 equals the integral of negative 1/2 x to the negative 3/2 dx, which is almost exactly, you notice this integral that I have here is almost exactly what I want to solve, right? The only issue is instead of a negative 1/2, I have a positive 1/2. Well, okay. So at the end of the day, we have f of x is equal to kq, big Q, over 2L. I'll put an extra negative sign in, right? We can just move the negative sign over to the other side. So I'll put a negative and a plus here. Okay. And so the final result of this entire integration process must be u to the negative 1/2. Don't believe me? Check it. Take a derivative of this function with respect to u. It's always good to, after you get done, check to make sure you get this piece back. So take the derivative of this and make sure you get that. Yeah, you do, right? Good. Now we're cooking with grease. I'll go ahead and put back in the original expression for u, kqq over 2L. And we have x squared plus y naught squared. It's a negative 1/2. And this will be evaluated at the limits, negative L to L. Now remember how we evaluate an integral. Yeah, top limit minus the bottom limit. So we have to substitute in L into our function minus our function when we put in negative L. Okay. So we'll go ahead and do that, but you probably already see what happens. Okay. So we have k q q over 2L. Okay. Then we have L, I'll leave it, L squared plus y naught squared to the 1/2 minus, right? This is the function evaluated at the upper limit. Now we have to minus the value of the function at the lower limit, negative L squared plus y naught squared to the 1/2. And now hopefully you see, notice I have negative L, but it's squared. And so at the end of the day, I get negative kq, big Q, over 2L. This term minus the exact same term. So I get 0. Like we already knew. Pretty cool, huh? Okay, so that takes care of the first integration. Let's tackle the second one. Okay. So we had f of y equals kqq over 2L, but now we had the integration from x equals negative L to L, y naught dx over x squared plus y naught squared. So the 3/2. Okay. Go ahead, chew on that one for a second. And right away, I should note, right away you know that the u substitution is not going to work. Because now, instead of having our integration variable in the numerator, we have a constant, right? So you can go ahead and try a u substitution, but you'll notice that you'll have this x that's floating around that you don't want. Okay, so u sub is not going to be the way to go here. Go ahead, try it. Yeah, good, good, good. And you hopefully ran through that list, but you see very quickly the idea would be a trig substitution is going to get you the right way. Okay? The hint is generally when you see something like x squared plus y squared to a 1/2 power, that's usually kind of an indication that a trig sub might be the way to go. Okay? Now be careful, if you had something like x squared minus y naught squared, square rooted, it looks like a trig sub. Those do not work out very well. Okay? You can try it again, but usually I find myself, I see one, I try to do a trig sub, and I spend like hours trying to do it. And then I look it up and find out it's like a hyperbolic integral or something. So it's always good to practice. But yeah, be careful. If that's a negative sign, this thing gets really ugly. So let's go ahead. Let's set up a trig sub. So let's go and we will call the hypotenuse x squared plus y naught squared, square rooted, right? That kind of naturally looks like the Pythagorean theorem, because it is. We'll say y naught, and we'll say this is x. And we'll call this angle theta. Okay. And so right away we see that sine of theta is equal to y naught over x squared plus y naught squared, square rooted. Right? So this will feel a lot like a u substitution, except that the function is more involved. It's not just like a power function. It's going to be a trig function. Okay, so this is kind of a category of u sub, I guess. So now what we have to do? Well, we need to take the derivative of both sides of this, right? We need an expression that says what theta is in terms of x. Right? We have to find that relationship. So let's go ahead. Cosine of theta, that's the derivative, d theta. Okay? And over here on this right-hand side, well, we have y naught. Got it? Yeah, good. I usually like to think of this when I have a fraction, a power in the denominator, I tend to think of it as a negative power that's in the numerator. So what this would be is negative 1/2, right? X squared plus y naught squared to the negative 3/2. So again, power rule. So I move the power in front and I decrease the power by 1. And now I have to chain rule it, right? I'm not done yet. I have a function inside a function. So I need to chain rule it, and so I end up with a 2x. Okay. Oh, goody, goody. Notice that the 1/2 cancels the 2 here. Okay. And there's another wonderful thing in here. So let me rewrite this. I'll write this as cosine. You know what, let me go over here because I'm going to want another line anyway. I'll write this as cosine of theta, d theta, equals, so now we have y naught over x squared plus y naught squared. And I'm going to write this a little suggestively, and I'll put a negative sign there. We have an x over x squared plus y naught squared, square rooted. Okay. Question for you. I've written this suggestively. I've broken this up. Thinking of our triangle, what is this underlying term? Yeah, you see it? This underlying term is exactly cosine of theta. Which means, oh, excuse me, and I dropped a dx here. Excuse me, shameful. I guess this would d theta dx. So I'll put a dx over here. This means that I can cancel the cosines, right? I can cancel this cosine with that cosine. Granted, they look a little different, but they're the same thing. And I get that d theta is equal to negative y naught over x squared plus y naught squared dx. Pretty cool, right? Yeah. And in fact, maybe I'll move the y naught to the other side. Let me move the y naught here. So I'll leave it like that, negative 1. Okay. Okay, good. So what do we have? Notice now we go back to our original function. We have f of y is equal to kq, big Q, over 2L, integral from negative L to L. And I'll write this slightly more suggestively now. We have a y naught over x squared plus y naught squared to the 1/2. We have a negative 1 over x squared plus y naught squared. And I'll put dx here. Right? And notice now this first term was just sine of theta. This second term was just d theta over y naught. So we're going to take these two substitutions that we found. That will go there. And this guy will go in right here. And you notice, boy, this makes it look a whole lot easier, doesn't it? dq over 2L, the integration of sine of theta d theta, and we picked up an extra y naught out front. And we're done. It's almost like magic, right? You go from this really complicated one to this really pretty simple one. Okay? Now, conceptually, what's going on here? Conceptually, when we set up the original problem, okay, it's not by accident this actually looks so nice. When we set up the original problem, we were thinking in terms of x and y directions, right? I mean, position of the bar, x direction, distance from the bar to the field point, y direction. Okay? We could have done this in a slightly different manner. Okay? So thinking about the position of the charge Q, you could think in terms of this instead. You could think, well, this relative position vector points at some angle theta. And as I move from piece to piece to piece to piece to piece, that theta sweeps out some angle, right? Starts at some angle, it sweeps to 0, and then sweeps to the same angle on the other side. Okay? And if we were to actually set the process up in terms of that angle theta, this equation, f of y, is exactly what we would have came up with. Q over 2L y naught integral of sine of theta d theta. Okay? So that trig sub is actually taking advantage of that. We could have written that down directly when we first set up the problem had we been a little bit more careful. Okay? Well, we'll go ahead. We can integrate that, no problem, easy peasy. We have a kqq over 2L y naught negative cosine of theta. And let's go ahead and substitute back in our expression for cosine of theta. Put the negative sign there. That was x over x squared plus y naught squared to the 1/2. Don't forget, we still need to evaluate at the upper and lower limits. Okay? Now I told you we started off with, shoot, what was I thinking? Oh yeah, we started off with an even function. Okay? So we know that at the end of the day, this should be twice the half interval value. Okay? So let's go ahead, let's evaluate this at the upper and lower limits. We just have this constant out front floating along, and we'll evaluate at the upper limit, L over L squared plus y naught squared to the 1/2. And then we always minus the function at the lower limit. So we have a minus sign, and now we have to plug in negative L for every place that we see x. Let me put the parentheses in there. And here you notice, again, in the denominator, we have a negative L squared. That's just positive L, right? And furthermore, notice that I have a negative, in the numerator I have a negative and I'm minusing it. So I have a minus minus, which would give me a plus, and I have this L squared here, this negative L squared, which should just become L squared. So if I write this all out again, and please forgive me, I want to be very explicit on what's going on here. I have L over L squared plus y naught squared to the 1/2 plus the exact same expression again. Right? I have two of them. And so at the end of the day, I can write negative kq q 2L y naught 2L over L squared plus y naught squared. Oh, goody goody. Sure, why not? Just for one last hurrah, you see the 2L and the 2L cancel. Okay. So yeah, you could do it that way. Cancel, cancel. So you have a couple of different ways. One would be the y component is given by negative kq, big Q, over y naught, 1 over L squared plus y naught squared to the 1/2. Or if you prefer, if say the charge of the bar isn't actually given. In fact, it's generally common with these distributed objects not to be given the charge, but to just be given lambda straight off. Okay? So in terms of the linear charge density, we could write this as negative kq lambda over y naught times 2L over L squared plus y naught squared, if you prefer. Okay? And we're done. So what have we done here? We have managed to find both the x component and the y component of the force of a charged bar on a point particle directly below the center of the bar. Okay? And no, are you going to have to do this? You really need to start kind of getting used to this process of taking a physical object and segmenting it up into pieces. Okay? That's probably the most important thing I can emphasize in this video. Okay? Yeah, is the math important? Yeah, it's important to be familiar and comfortable with integrals and different integration techniques. But at the end of the day, the truth is, more of usually the really interesting and important problems, you can't actually do the integration anyway. Okay? Most of the time, these integrals get really bad. Okay? And so you're either looking it up in a table or you have to have a computer do it numerically. It's called numeric integration. It literally goes through and does the small values and adds them up for you, like we did in our Excel spreadsheets. Okay? So, but the issue is if you want to tell a computer to do that, you have to be able to program it in. In other words, you have to know how to set up the entire integration process before the computer can take over. Okay? So I think that's probably the most important piece of this whole discussion, is that practice of taking objects and dividing it up and actually setting up the equation. Okay? Cool. Well, I think that's probably enough for this video. I'd say keep up the good work. Make sure to ask questions. I'll see you next time.